Oh, I appreciate it. All right. I want to finish up what we need to learn before the test, and then I'll talk a little bit about the test. So, last time we talked about how you calculate expected value of a function of a random variable, right? Yes. And basically we did a weighted average. We did the sum over everything in the sample space of what? Chelsea.
Chili.
What do we take the sum of? Good. G of x times f of x. Remember, the f of x is your PMF of x. So basically what this is, it's a weighted average. Your f of x is giving you the probability that the value of x happens. Right? The f of x is giving you the probability that f of x happens. So this is giving a weight to how often the g of x is going to happen. It's giving you a weight of that g of x. Adding it all together takes an average. That's what we're talking about, the expected value. So it's a weighted average of that function. So in general, if we want to know on average, what the value of x takes on, if you repeat the trials over and over and over again, that's just the expected value of x, where the function is just g of x equals x. So that would be your sum over all your points in your sample space of x f of x. We talked about that last time, right? So again, your f of x is giving a percentage of the time that you would expect the x to happen. When you add that up over all your x's in your sample space, it gives you an average of the x's that occur. So for example, if I roll a die over and over and over and over again, each number on the die has a 1/6 chance of happening. So 1/6 of the time it's 1, 1/6 of the time it's 2, and so on up the line. So if I take the sum of 1 times a 6 plus 2 times a 6, and so on, I'll get 3.5. This is what you would expect if you roll a die over and over and over and over and get an average, right? Because you would expect about as many 1s as 2s as 3s as 4s as 5s as 6s. So you'd expect an average of about 3.5. That's the idea for your expected value. Now, another thing that's an important thing to be able to compute from expected value is what's referred to as the variance. So we use a Greek letter sigma and then the square to talk about the variance of x. This is the expected value of x minus the mean squared. This is the definition of variance, by the way. Okay? So what we're doing when we do this calculation, your expected value isn't, think of it as an average of something. What the variance is trying to measure is how far, on average, is each individual point in your sample space away from the mean. Okay? If I didn't have this squared here, let's think about what would happen before I do an example with this. If I just had expected value of x minus mu, for example, if that's all I had, then by definition, this would say this, right? Because the x minus mu is my g of x. What can I do with the f of x relative to this minus sign here? I got sf of x outside these parentheses. What can I do? Oh, there's a good word. I'd have that, right? And now I've got a summation with a difference in the middle. So what can I do with this difference, with this sum relative to that difference? I can split it up. Now, this x is not a constant, right? Because this x changes, correct? Right? Because that x changes that, so this is not a constant. How about this mu, though? Is that a constant? Yes. So what can I do with it relative to the sum? Yeah. Pull it out in front, right? Oops. Right? We agree? Okay, now look at these pieces. First, let's look at this last one. What's f of x again? The PMF, right? This says take your PMF and add it up over all possibilities. If I take my PMF and add it up over all possibilities, what do you have to get? 1, right? So this last part is just going to be mu. This first part should look familiar. What do we call this first part? Yeah, it's the mean of x. It's mu, right? So the first part is also mu. We get 0. So if you've had a statistics class in the past and have done some calculations with variance and standard deviation, the reason you just don't use x minus mu to try to figure out your average distance is because you're always going to get 0 when I add that up. Every single time. This is called the sum of your deviations over a data set, if you will. But you will every single time get 0. So that's not a good measure of how spread out the data are. Right? Because every single time you get 0 and you add that up. So if I want a measure of how far away each data point is from the mean, we do the difference and then square it is one way to do it. Okay? So this is our definition of variance. This is literally the definition, and it's also not very often that we actually compute it this way. Okay? So let's talk about how we typically compute the variance by working with breaking this thing apart. Okay? So in particular, let's look back over here again. Notice that I did an expected value of x minus mu, and I was able to break it up over that minus sign. That's true in general. So, as a theorem, the expected value of a times g of x plus b times h of x is the same thing as a times the expected value of g of x plus b times the expected value of h of x. There's not a lot to prove here. I just go through the definition and see what happens. Well, the definition says I take that function. Oh, crud. Ashlyn, do you have your charger? That was awkward. I'm glad you had your charger. Well, I had to run downstairs real quick. Or not record it, one of the two. I just take the function. We take the function and multiply it by the PMF, right? That's just the definition of expected value, right? What did we do in the first step above? we took the P of F and we distributed it, didn't we? Right? That was the first step that we did in the previous part, didn't we? What did we do next? We split it up at the middle sign, didn't we? It's a lot of letters, but it's the exact same process we did in the previous part, isn't it? Nothing different, right? What did we do next? We said we noticed we had a constant, so what can we do with the constant? Take it out in front, so that those A and B's, the A and that B is a constant, we can pop it out in front. And then we said, oh, what did we do at the end? Well, now I have function times PMF. That's just the expected value of that function, right? Same thing over there. So we're done with this proof because it's literally what we wanted. This is A, expected value of G of X, plus B, expected value of H of X. We'll do an example using this formula here in a minute. I want to get back to the variance. These are the two big ideas that I wanted to talk about today before I talk about review for the test. But we refer to the expected value operator, this E operator, as a linear operator. All that means is, the fact that it's an operator means that it's working with functions. So you don't have to worry about the word operator nearly as much. The linear part just means that it breaks up over sums and differences and constants pull out. So you've dealt with other linear operators before in other classes. The limit operator in calculus is a linear operator because limits break up over sums and constants pull out. The differential operator, the derivative operator, is a linear operator because it breaks up over sums and differences and constants pull out. The integral operator is a linear operator. Okay? So this is not your first experience with linear operators, but things that break up over sums and constants pull out. Okay? It's just another one in that class. Things that aren't linear operators, for example, the sine function is not a linear operator. Sine of x plus y is not sine of x plus sine of y. Okay? So you've had things that are linear, things that aren't linear. All right, back up to variance. Another notation that's often used for variance is VAR of x, just to give you another notation. Oops. Again, this is the actual definition of variance. But again, in practical purposes, this is not how the variance is computed. Okay? So let's use those properties that we just talked about to see how the variance typically is computed. This is a minus, this is a difference squared. What do you think I might want to do to help me simplify? Square it out, good, FOIL, yeah, expand it. X squared minus 2x mu plus mu squared. Right? Okay. What did we just say we could do with the expected value with respect to sums and differences? Break it apart, and we can pull out constants, right? So this is expected value of x squared minus 2 mu. Come on, erase. Expected value of x plus mu squared expected value of 1. I did that on purpose. Literally just went through, broke it up over the sum and the difference, pulled out things that I knew were constants. 2 was a constant, mu is a constant, mu squared is a constant, right? When I pulled out the mu squared in the other part, that said expected value of 1. Well, let's think about expected value of 1 for just a second off to the side here. That would be our formula for expected value of 1, isn't it? Well, does that 1 here really matter anything? No. So what does this say to do? Yeah, it says to find what? The sum of the f of x over all possibilities. What did you just tell me a little bit ago that was equal to? 1, yeah. And in general, the expected value of any constant is just that constant. Because all you would do is just factor it out in front of the sum, just like I did with the mu squared. Yep, E of 2 is just 2, yeah. Because over here, expected value of mu squared is going to turn out to be mu squared. It's just the constant. All right, so in my next line here, I'll write expected value of x squared minus 2 mu expected value of x plus mu squared. Oops. What was another name for expected value of x? Mu, right? So all I did from this line to this line is replace expected value of x with mu. So I have mu times mu squared. So I've got 2 mu squared minus, and then plus another mu squared, right? So this is going to simplify to expected value of x squared minus mu squared, or written another way, it's expected value of x squared minus expected value of x quantity squared. So this is the typical way of calculating variance. So let's do one. So let's say I gave you a PMF that looked like this, where I've got my x. The only possibilities for x are 3, 5, 8, and 13. And then those are the probabilities associated with those values of x. How are we going to figure out what expected value of x is, or what mu is? What do we do? We do the sum of x times f of x, right? So in this case, what will we multiply together? 3 and 0.2, 0 and 5 and yawn 0.5, 8 and 0.1, 13 and 0.2. Right? So exactly how we would compute mu, or expected value of x. Right? We agree? Yeah. Okay, cool. All right. So we would get 0.6, what is that? 2.5, 0.8, and 2.6. Oops. Plus 5.1, 6.5. If I did my arithmetic correctly. Never trust my arithmetic, but you're always right. Not always right, trust me. Decimal point in the wrong spot where? Where's my decimal point in the wrong spot? It's like, where's my decimal point in the wrong spot?
I was thinking it was 0.5 times 0.5.
Oh, it's 5 times 0.5, yeah. All right, so again, this is mu. That's just another name for the expected value of x, right? That's our mu. We agree? All right. So if we want the variance, the first thing we're going to do is compute the expected value of x squared, and then use our formula we just derived above. Okay? So let's do our expected value of x squared. The only difference between expected value of x squared and expected value of x, here are our x values, right? The 3, the 5, the 8, and the 13. The only thing that we're going to do is square them. Yeah. The f of x is your probabilities. Yeah, it doesn't change. This one oh, what do you get? 9 times 0.2 is 1.8 plus 25 is 12.5. This is 6.4. 169 times 2 is what? 338, so 33.8. So what do I get? 40.2, 52.7, 54.5. So what you got? Cool, good. Thank you, Martin. That's not mu squared. That is not mu squared, definitely not. Because mu squared would be, what, 6.5 squared, right? That's not going to give you 54. 7 squared is 49. So you're going to get 54.
So the sample result should be variant, the x squared, or always be bigger than the
Yes. The only thing it could be is 0. It can never be negative. Yeah. All right. So when we want the variance of x, or again the sigma squared, that's expected value of x squared minus expected value of x quantity squared. And again, like Sam said, this expected value of x squared has to be bigger than expected value of x quantity squared. This can never be negative. Okay. Think about why. Think about how this is computed. Remember, expected value is that you take the function and multiply it by the probability, right? And then add it up, correct? Is this ever negative? No, because we're squaring. Is probability ever negative? No, because it's probability, right? And if I add things that are not negative, can it ever be negative? Probably. Probably not. Okay? So this always, always has to be greater than or equal to 0. And the only way it can ever possibly equal 0 is if you have basically a one-point space. If your x value can change, then it's never going to be 0. The only way it can be 0 is if your sample space is one element, so it has a 100% probability of happening. It's the only way you can have no variance. Okay? All right. So for this one, then you get 54.5 minus 6.5 squared. Anybody type that in? Thank you. Cool. That's how you calculate variance. It's a matter of memorizing that formula. This one right here. Yeah, you don't need to know the theorem. We're going to do an example with using the theorem here in a minute. Yes? So variance is a way to calculate on average how far or how spread out the data are. So how far things are away from the mean. Now, of course, to do that, we squared things, right? So it's not really, the on average part is the expected value, but we squared things to make it not negative. So the way we adjust back to calculating kind of how far on average things are away from the middle, how spread out they are, is we do what's called the standard deviation. So you led me right into it. So the standard deviation is, it's the square root of the variance. It's a way, it's not really undoing the squaring, but it's a way to undo the squaring. Okay? So we did this, because when we said when we just did the adding up of the deviations, how far each point was away from the mean, we got 0, right? So just trying to do an average deviation isn't going to work. So a couple of natural ways to take things from being positives and negatives to all positives are doing absolute value or squaring. There are advantages to doing squaring over absolute value, one of which is absolute value's got corners, which makes it not differentiable. And later on we're going to be doing derivative stuff and want to make things differentiable. So we do the squaring to get rid of the negatives. But then we have to kind of undo the squaring if we really want to measure how far on average something is. It doesn't quite work, obviously, because this is a sum of squares, and square roots don't break up over sums either, but it's the idea behind it. But it's a measure of spread, because we're doing point minus mean. So it's a measure of how far things are away from the middle. Or not the middle, but the mean. That's what it's doing. We're going to have a lot more discussions with that later on, and especially if you take second semester next semester. Yeah, I can. Where do you want to go to? 2:30 we talk about it, 3:14 we talk about it too. Mathematical statistics.
Which one do I say?
Both.
So, since the standard deviation isn't quite perfect, why don't we take the square root before we add them together, so it's not the square root sum?
Because if you do the square root before you do the sum, then you do the square root of the square, you get absolute value. So it's like you're taking the absolute value of these terms. Because when you do the square root of if I do the square root of x squared, I get absolute value of x. Because if it's negative, the squaring will make it positive. When you take the square root, it keeps it positive. And so you can actually do that. That's called the mean. It's called the mean average deviation. Mad. It's what it's called, but it doesn't have as nice properties as what the variance does. That comes up later on in more advanced stuff. So that's why we use the squaring method rather than the absolute value. I know it's not a very satisfying answer right now, but there's a lot of other machinery that has to get built up to be able to see why we actually do the squaring rather than the absolute value. But probably the easiest thing for right now to understand is that absolute value isn't always differentiable, right? And squaring is. So that's why it's a bit better. It's also, there's actually a theorem that I'm not going to talk about, but in the book, it's theorem number, or I'm sorry, it's example. It's example 2.24 on the top of page 65. And talks about this particular idea with an arbitrary constant in here, and that this is minimized when you get to the mean. So it actually does the derivative. I'm not going to talk about it because I'm not as worried about it. It's more of an important thing for next semester. But it gives you another reason why we like the squared part. If you're interested in it. This process of being able to compute the variance, okay? Just doing probability times the value for x and being able to do the variance is okay? Wrong name, sorry. Megan's right next to you.
So, like, an example problem we would be given our x
Yeah. Or you'll be given a formula for the PMF and then plug the x's in. Like,
right.
Like if you had, I'll pull one out here. You've got one of the ones, I think we started one last time when we did the 2.3-1c, where your f of x was 4 minus x over 6, where x is 1, 2, or 3. So you do the same thing with that. In that case, you would 1 times the 4 minus 1 over 6, or 2 times 4 minus 2 over 6, you have a formula plugged into the table. Same idea. Let's do an example where we use some of the theorem that Megan had. This was Megan that time. Megan asked me about if we're going to do an example with the theorem. Yes? Yeah. All right. All right. So let's say that X has a mean of 13 and a variance of 12, and Y has a mean of 17 and a variance of 30. I'm just making up numbers. Doesn't matter. Start with a straightforward one. Let's say I asked you for expected value of 7x. What can I do? What's one of your properties of expected value? Pull the 7 out. And do we know expected value of x? What is it? 13, yeah, because we're given the mean is 13, right? So I can pull the 7 out and just plug in the 13 for expected value. Let's say I wanted the expected value of 9y minus 2x minus 6. Yep, I can break it up. How would I break it up?
9.
Put that down. 9. Okay.
Minus 2 minus 6.
Good. So I have to write a 6. You mean the E of 1 part? Yeah, you don't have to write that part if you don't want to. But you definitely have to write the 6. That part is important. The E of 1 is 1, so you don't have to write that part. All right, so then we see when we're using the theorem here, right? We're breaking it up, pulling out the constants and breaking it up over the sums. Right? So then what are we going to plug in for E of y? 17. And for E of x? 13. 121? 121? That seems low. It is 121. Okay, this is low. Sorry. My bad for... Oh, I know I did it wrong. My bad for doubting it. Sorry about that. Seemed low. The process okay? Okay.
Is this how it's going to be on the test?
Is there how does it work on the test? This problem? It's certainly a fair game for the test.
Is it going to be this easy?
This is certainly a fair game. If you find that easy, then yes.
All right.
I'm not sure how to answer that question.
You're gonna try to spruce it up a little bit and make it harder. Is that better?
That's just 900.
I'm aggressive.
No, it's not just 900.
And 611.
Well, how did you come up with 611?
The variance minus 7 squared.
I wouldn't give you 611.
Variance squared.
You did the square, yeah, you squared the variance. That's not 611 either.
Would this be? Let's say it's the variance minus the variance squared minus the mean squared?
Not quite.
Is it the same?
Thinking around the same line, the right lines, but it's not just.
Is it variance plus square?
It is, yeah. It's just the variance of y plus the expected value squared. You're exactly right. Yep, because this would have been subtracted over for the formula, right? The variance is expected value of x squared minus expected value of x quantity squared. It's just shifted. It's just solved for squared, right? Look back up at your formula. Where is it? There it is, right? We've just shifted the expected value of x quantity squared to the other side. Right? So that's your variance formula, right? Just move it to the other side. That gives you expected value of x squared. Tricky, tricky. So the variance of y was 30, is that right? There should be a y in here. And expected value of y, what did I say was it? 17. So 289 plus 30 is 319? Yep. If I did it right?
Yeah, only 600 off.
You were just 600 off, just a little bit, just a tad. Let's try this one. This might be as tricky as this one gets, by the way. Give you a hint, go back to your formula of how you would compute it if you were actually just going to compute it. Do that first. Go to the formula.
This one takes a little bit of work.
A little bit, but not, it's not horrible.
I don't want to do it about
Killing it? Is that what you said?
What did you get it from?
Well, that sounds like.
Except that I treat the inside like it's a variable, so I square it. So instead of just square root of 6 minus 3 over 1 squared. Dr. Joe, what's the variance for x above the top?
Yeah.
It was. No, look.
What was it?
Yeah.
Oh, 12. No. Yes.
Does it start with the 4?
Yes.
Does it add add with octopus?
Similar to that, yes. Or snowman. See, she got it.
I think I got it.
Oh, that's right.
There's a reason why I didn't put numbers in. To show a more general result. So the crux of this one is that I just use the variance formula, but I treat my 2x minus 3 like it's the variable. So I do expected value of 2x minus 3 squared, and then minus expected value of 2x minus 3 quantity squared. Take the 2x minus 3, treat it like it's the variable, and then just simplify, well, expand, I should say. Foil out a couple of times, right? Foil out on the inside here with expected value. Foil on the outside here with the expected value, right? And then break apart the expected value, just like we have been. Now, one of the reasons why I didn't bother putting in the numbers for expected value of x is because I wanted you to notice something. Notice that when you FOIL out the 2x minus 3 in here, you get a minus 12 in the middle, and then the minus 12 pops out in front of the expected value, right? Notice the exact same thing happens here when you FOIL it out. The 2 and the minus 3 are the same FOILing, right? So you get the exact opposite signs on your expected value. That cancels, right? And notice also, here I have to square the 3 to give me 9. Here I have to square the 3 to give me 9. The expected value of 9 is just 9. My 9s will cancel, right? So the only thing that we're left with is the 4 and the expected value of x squared minus expected value of x. Oops. Minus expected value of x squared. But what is that? What is another name for that? That's the variance of x, isn't it? All right, so let's look at where the 4 came from. Where did the 4 come from? Squaring the 2 on the x, right? So the effect of the constant in front of the x makes a square in front of the variance. Whatever that number happens to be. Didn't matter that it was a 4, right? I could have replaced this with an A and would have got an A squared there. What effect did the 3 have? Nothing. Now think about why that is. Variance is a measure of spread. We don't even talk much about it, but that's what variance is. If I multiply numbers by 2, it's going to spread them out more, right? If I double their size, it's going to double, well, it's going to actually make 4 times the spread, right? It's going to spread them out more, right? We'd expect that to happen. But if I shift numbers, does the spread change? Do they get more spread out if all I do is just pick them up and move them to a different spot? No. So the minus 3 doesn't do squat to the variance. It doesn't spread them out any more or any less. It just shifts it. You learned about vertical stretches and shifts and horizontal stretches and shifts back in algebra class with graphs, right? You see how the graph gets stretched or shrunk when you multiply by a number, but if you take a number and add or subtract it, it just moves it. It doesn't stretch it or shrink it anymore, right? It's the same concept in probability and statistics. It doesn't do anything. Shifting it doesn't do anything to the spread. Keep the same spread. But if you multiply it by a number, it does stretch it or smash it, depending on what you multiply it by.
I just want to clarify, you said it doubles it, it doesn't square it?
I said double it is not the word I meant. I was thinking the 2 was doubling. You know, it's squared whatever you're there. It's squared. It definitely squares. It squares the constant, multiplies it by the square. All right. All right, so a little bit about your test. So you'll need to know, of course, your different properties of probability, with probability being non-negative, and if you take it out, add it all up and over the whole space, you have to add up to 1. Your probabilities of complements and unions and those kinds of things, right? So some of the bigger formulas from that, of course, were if you do the probability of a complement, that's 1 minus the probability. Probability of a union. Split it up that way. Right? You can extend that to 3 sets. It's a lot of writing. You've had homework problems that have involved those formulas, right? You also had your conditional. Those are conditional probability formula. And then we also did those problems with Bayes' theorem. We talked about how to rewrite the denominator in those cases, right? To be able to flip your conditional around. Certainly ones like that. We also talked about independence. So when we have independence, we can just break up the and as the product of the 2. Yeah, you can. Yeah, there's counting stuff too. Yep. It's hard to do discrete probability and not have counting problems. Oops. We also have the idea of mutually exclusive. You certainly might have counting problems, like Sam just asked. So multiplication principle, permutations, combinations, those things. And then, of course, the stuff that we just had with the probability distributions. That is an ugly way to write the word distribution. And then we just did the stuff with expected value and variance and standard deviation, showing how to do those things. Again, standard deviation is just square root of variance. So if you see a problem with standard deviation, find the variance and then take the square root. Yeah, mark it.
There are going to be any groups on there?
No. You want some? I can put it on just yours.
No. That's why I said. Alright, I don't know. You can find out
I can prove All right, have a good one. We'll see you tomorrow. Remember, no class Friday.
That's always positive. I can drive a little bit more after I get done taking the test.